Hello everybody. Today I want to talk about this, and by this I really mean this, which is my favorite hobby, which is radio control cars, and this happens to be a 1/10 scale rock crawler. Now it's very aesthetic in this current form like this, and I want to give a shout out to the two GrabCAD sources that I used to do a couple of these things. Firstly, the shell I got from this model here, the Toyota Tacoma model here, and which is a mesh. It came in as a mesh. And the other one I used for the tires and wheels is this one here from a Jeep Wrangler, also an RC car. So GrabCAD has proved a very valuable resource for this, and I've used it to great extent. So I'm going to hide them for now because they're distracting from what I really want to talk about, which is this assembly. And it's a reasonably complicated one because there's so many linkages. It has motion in it, and when you tackle something like this, it's often really, really difficult to know where to start, because you sort of chase your tail sometimes, or it's a chicken and egg situation sometimes where linkages are going to be, what length they're going to be, and you can end up in CAD systems creating some very, very nasty circular references. There are techniques to try and avoid that, and Onshape is particularly good at providing such techniques. So I'm going to talk about some of those today. I fear this is actually going to be quite a long one, and I want to be in bed by midnight, so that's going to give me a bit of a challenge. Anyway, let's start right at the beginning. And by the beginning, I really mean all the way back here. In fact, let's call it a system level skeleton. Now, I like to use these kind of skeletons and flow things down top down as much as possible. Now, whether you're doing a vehicle chassis like this, with there's lots of linkages, or whether it's some kind of robot or machine or just about anything really which has got a complicated assembly, these techniques are going to apply equally well. So usually there are some really specific requirements for hard points for the very top level system specification. These might be the wheelbase, the wheel track, the height, the radius of the wheels themselves, and all sorts of other, high level requirements that we need to meet. Now, if you do anything like this more than once, you find that it's very worthwhile doing some automation around it. So, of course, knowing me, I've probably built, or I have built, a custom feature to help me automate some of this really early kind of sketching out of these hard points. I've actually got my own custom feature here, a really, really simple one called the chassis base data. And if we have a look at it, you'll see that it's a number of pages of really just entering data. Like almost, you can just enter the wheel overhang at the front and the rear, the wheelbase, the overall vehicle length. These are calculated from other things. So the chassis height. And then there's a section on wheels. So the front and the rear wheels have different aspects here. So, typically, and I'll take it out of perspective mode for the moment using my favorite shortcut. I loved using this, going in and out of perspective mode. I work pretty much exclusively in perspective mode, but I realize that sometimes it's not easy to follow. So I'll go here for this. For example, on the front camber, I might want a very high negative camber at some point. So it's very easy for me to just type in values here. And at my skeleton level, you'll see how these really gross, large-scale space claims, if you will, are being updated there. So let's just go to straight up and down for the moment. And I've got similar sort of pages here to ascertain the position of where the motor is going to be or the steering axis is going to be, and very simple one about the length of the shock. Now, some of these are actually also being driven by variables, global variables. I've got a variable studio here that sometimes is very useful to pass variables into multiple different part studios or even assemblies in the model. And I've used that here to provide a couple of those. I think there's, wheel diameter is another global variable there. So let's not dwell any further on that, because let's focus on, now that we've got these positions and specific, now I use mate connectors as a really, really powerful way to provide these hard points. A mate connector, as you know, is a multi-purpose powerhouse, let's say. It is a point, it is an axis, it's a plane, and it's a coordinate system, all in one, right? And it's a really, really convenient way to capture all of that with the minimum amount of construction geometry. You'll see here, compared to, as we go along through this, eventually, the amount of construction geometry I use in this kind of a model compared to what you will probably be familiar with in other systems, in traditional systems, it's very much more minimized here, because I use mate connectors and use them in their multi-role. As I said, I think they're a real powerhouse. Anyway, so this very first part studio just consists of, the first thing on every model is, for something like this, is a vehicle coordinate system, and that is a mate connector down here. So I've put that down at the origin for now. Some of my calculations are always based on the bottom of the wheel underneath the front axle, right? So that's the reference coordinate system that I will use throughout. It doesn't have to be, and the reason I use this as a separate mate connector is that maybe I'm going to change the reference later on to be something on the white front firewall or whatever else. Anyway, so we've got this, we've got our base data, which the base data custom feature created these wheels and these other mate connectors and a couple other things that might not be visible at the moment. I've created a really rough sketch, which is going to provide some kind of guideline for the chassis rails. It's actually coming on this plane here. And then I've got my second, I'm only using 2 custom features in this, and we've already used one of them. Now let's use the second. Like a lot of systems have, there's a really useful technique to use for top-down design called publish geometry. Now, I know that at least 2 that I've used before, 2 different systems, have something called publish geometry. And directly inside Onshape, there isn't something that says it's publish geometry. But there's 99.9% of the workflow is possible with 2 things: the composite part and the derive feature. So these 2 things together make up effectively what is published geometry in other systems, except for one fact that led me to create my own custom geometry, published geometry custom feature. And let's have a look at one now. Before I show you, I'll just tell you the reason why we need to publish geometry from this level. From the skeleton level, and we want to pass references down the chain, there's a really convenient way of doing that, and that's to collect certain faces, certain curves, certain sketches, certain bodies, and package them together into a composite part, and then in another document even, or another part studio, we can derive in that composite part and then start using references from it. This is super convenient for a number of reasons. One of them is that, again, you can cross between documents. You can version manage this thing because it's a composite part. You can release manage it. That's a really, really powerful thing. I won't go into too much today, but release management of the composite part, which is carrying the references, is a hugely robust way of doing things. It's really, really deceptively simple to do in Onshape, but it is also the topic of many, many pages of help in other systems that use this type of technique. And it's much easier in Onshape because the PDM is built in, of course, but again, let's not go into that right now. So the only difference between doing a composite part and selecting entities here using the native feature and my published geometry custom feature is pretty evident from the start here. Firstly, I've split in the selections into different categories. Firstly, surfaces and faces, bodies, curves, edges, sketch features, and really, really importantly, mate connectors. So I also have a name for them, and I put this name up here because this is going to be the name that we generate down here for the composite part. So as you'd imagine, I just collect up the references that I need, and I'm doing this published geometry for a very specific functional area, which is the front suspension or front axle. So I need these two front wheels, I need the vehicle coordinate system, which is this first mate connector, I want the steering axis mate connector, and I want the two wheel center points mate connectors as well. So that's all of the published geometry that I need so that I can go off and start doing more work on the front suspension. If I just hide a few parts and hide these other ones here, you'll see highlighted in magenta, my custom feature here makes this sort of a translucent magenta color, just so that I know it's a published geometry. So you can see I've got one for the front suspension, I've got one for the rear axle, which is a different set of references, but it does include the same vehicle coordinate system as a reference. In pretty much all of my published geometries will include this vehicle coordinate system mate connector. So, and as you can imagine, when we work on these things separately, in separate documents, in separate time zones, and they come back together, they will always come back in the correct location. That's one of the reasons for doing it this way, for structuring it this way, as a top-down approach. So, to summarize in this first system-level skeleton model, it's a part studio. It contains special hardpoint geometries and a few really key space claims. Now, this is, I could have done a lot more in here, but I'd really like to try and keep these skeleton models as simple as I possibly can, and only pass down the line the references that I really need. So, I talked a bit about the rear chassis, the rear axle published geometry here, which consisted of these two and this one here. Let's go and see how it was used in its part studio, which is conveniently here called the rear axle skeleton. All right, so let's switch over to that. And you'll see here that this also is a really, really simple looking thing. You'll see that the vehicle coordinate system is out here in front, and I don't have any other references other than the normal front, top, and right datum planes, the construction planes that are in every part studio here. The first feature is a derive feature, and this is where I'm deriving. If I edit this, you'll see I've derived from the system skeleton, and I've derived this publish rear axle. This is the second really big reason that I created my own custom feature for this, is that it allows me to sort of really collate all the references into a single pick. I'm picking this here. I don't have to look through and say, I need that sketch, I need that wheel, I need this one, I need this. No, I just do it one time, and it's very easy for me to come back at any time, or the system modeler to come back in here and update this published geometry feature. They could come back in here and add a couple more things to it as required, make corrections, maybe re-release it, and then the people downstream, like this rear axle skeleton modeler, is able to get the benefit of that. Right, so this is a part studio, and it contains around about 20 features. So these are really super lightweight things that just don't take any time to regenerate. And this is one of the reasons to split things up appropriately as well, so that you can keep things regenerating really fast and not have multiple redundant references going over and clogging up the pipes, so to speak. So what I've got in here are the original set of hard points, and I've started building some really, really simple things. Let me roll back and show you the kind of things I built. I built a curve, and I built a sketch which might then be revolved into a really rough space claim for the center of the differential. Don't worry, this is going to get a lot more detailed later on, and you'll enjoy that. But for now, this is all I really wanted. This is just a space claim for where these will go. And the same thing with the axle centers, or the axle tubes here. I'm just roughing out kind of rough space, getting an idea, and then I'm going to use these again, down the line. I started creating a whole bunch of new mate connectors here as well. So as the rear axle skeleton designer or system level person who's in charge of the rear axle, I'm starting to rough out some key points in here in my subsystem, such as where the spring, the bottom of the shock absorber will mount, and where the end links will be for the suspension links. Now, these aren't sort of appropriate to put in at the system level, or maybe they are, maybe they aren't. But in this case, I decided to put all of this kind of detail in at the at this rear axle skeleton level. Did a couple more mirrors, and then I did another, and this is where it starts getting really fun, is that you can derive in from different sources other bits of published geometry. So in this case, I have brought in, and let me highlight this one for you, and using the isolate feature, you'll see that there's a bunch of faces that look like the core of a differential. You can see the pinion and the ring gear here. These have actually come from a completely separate document, right? And these represent like the really basic outline of what is really a complicated piece of geometry in here. And I can show you that geometry later on. But for all intents and purposes, or what I need here, are the positions of these bearings, and the size of those bearings, and the clearance that I'm going to need around this bevel gear, ring gear, and the pinion here. So I don't need to bring in a whole bunch of really complicated things. It's a pretty complicated model over there, but here I've just got some simplified things that I'm going to be able to use to pull off references and then keep passing them down the line. It's a whole game that you want to play where you only pass the references that you really need for any one particular given task. All right, so I brought those in, and the reason I wanted to bring in this at this level of skeleton here is so that I could pull out this very important mate connector, which was part of that published geometry. Right? You can see how everything is starting to fit together here, and the reasoning behind all this. So I wanted this axis, I wanted this point, and I wanted the plane as well. So what better object to use than a mate connector here? Then I probably did one more mate connector. There it is. So that represents, and then I built few little pieces of geometry that represent the skeleton of what is going to become a detailed rear axle eventually. All right. So I did the same sort of thing for the front skeleton. The first thing I did was derive in from my system model the hard points, and this is we're at the front axle now, so you can see that the vehicle axis is right underneath us. There's a lot more interesting stuff going on the front, which is the steering. Now, again, this is stuff that is not appropriate to be asking the system level person to be doing. This is the job of the sub-assembly or the subsystem person who's in charge of the front, and steering is a big part of that. So there's a very important few variables that I've captured here at this level. You can see some global variables that are being passed into me: wheelbase, shock length, wheel diameter. Some of those are pretty relevant. But then I've got also the kingpin angle and a caster angle. Now these are also things that I have set as variables, and you can see here that the axis of the kingpin is tilted back in the caster, and it's also tilted in like this. It's pretty, it ends up being, an interesting looking thing when the steering is operating. And this is always very good to rough out and make the skeleton of before you dig deeply into the many features you're going to need to create the steering knuckle and the uprights and all of those things. So again, I've used variables to help drive that, and I've used variables at the appropriate level in here. And again, I've imported I've derived in the differential core just like I did for the rear skeleton. This, of course, is a four-wheel drive. Now, the last of the main skeletons is for the chassis, and this is the one that it's a kind of a hybrid between a skeleton and some level of detail. And the level of detail here is the chassis rails. It just made sense, they were so simple to do at this point that I didn't really need to split, into skeleton plus detailed. But there's a lot of other really, really interesting things going on in here. Again, being driven initially by the system skeleton. Remember, we're bringing things in from here. I've derived in some very, very important positional data from the servo mounts. Right, so these here are where my servo, it gives me the pitch or the distance between the fasteners that the servo is going to use. And talking of that, this mate connector here, remember, came all the way from the top level system skeleton, which is the steering axis, which of course, needs to line up with the servo as well. So this is the point where we sort of start bringing together some really fundamental datums and a little bit of construction. You can see here I've done, connecting some dots together between the wheel centers, the wheel and the road location, and the length of the shock absorbers, and these are other things that are being driven by those very early structural hard points. Now, in the middle is the most complicated stuff. Is in the middle here. Now, this sketch that I've got here, there's two sketches on different planes. These are for the skid plate, and it's also where the suspension links are going to join. Now, capturing this at a skeletal level is really, really important because I'm going to be able to drive this without getting myself tied up in circular references. And this is really, really the best and perhaps only way to do it. The other thing that is doing here, it's allowing me to pass down these key fastener locations as well. So it allows me to define where these suspension uprights will be fastened on the chassis rail. This is also where the skid plate and suspension mounts are going to be fastened on the chassis rail. So I can throw in some whole features to do that, using these same references, but at the same time, these are going to be passed down the line to the detailed design. Now, speaking of that, you'll see a bunch of additional published geometry features in here. In fact, there's approximately, maybe exactly 6 more custom feature usages of the published geometry custom feature, which is essentially me, using the composite part to bring together a whole bunch of references that I need to create some of my detailed design. So let's have a look at what I did for the skid plate, because that's probably the most complicated and interesting one here. So if I edit that published geometry, you'll see, of course, let's always start with the mate connector out front, which is the vehicle reference system. I'm going to keep that one absolutely, robustly the same throughout all of these skeleton as well as detailed models. All right, so that goes without saying. The other references I need are some inside faces here. I'm going to bring the inside face of these chassis rails, and that's effectively giving me the exact, it is giving me the exact distance between these two rails. So should we go all the way back to the beginning and change some of these, the chassis width, then I don't have to worry about the skid plate falling out because it will always be using these references, which are 100% robust through here. So there's two faces there. The other thing that I have chosen are these sketch features. So I've chosen these two sketches because these corners represent the center point of where the ball joints of the suspension links are going to go. So you can see how this is all passing down the line. Now I've actually created that published geometry and given it a name, publish for skid plate. Let's have a look for that in a second. But before we do that, I'll just point out that these mate connectors that you see here, which are all oriented in the direction that I want, these came after the sketch. So I drew the sketch first, and it just provided me a very simple, easy way to select these endpoints and direction to create these mate connectors. And you'll see that I probably have named them carefully up here. This is the transfer, the gearbox, the transfer box output for the forward axle, and this is the rear axle here. This is the transfer center. I always use very carefully, naming things so that if we come back ever, you don't lose track of what you were thinking, last week or days, hours before, whatever. I also use colors. You can see here sketch colors. Some reds here. Some of these reds are from projections, and some of the blues are my primary sketches. I have my own color scheme in my head. You don't have to use it, but I do encourage you to use sketch colors for the things that you really want to stand out. That red projection one here was actually the edge of the surface that I'm using. These chassis rails aren't just straight. You can see how they actually, if I go into, you can see here that they actually sweep along and then move out and move back in again. I used a sweep feature for this, and there's a sweep feature somewhere back here. There's a sweep feature here, and you'll see here I've actually kept profile orientation so that it doesn't twist around as it goes down the sweep trajectory, which is not planar. There we go. So we have created 3 big skeleton subsystems for the rear, the front axle, and the chassis itself. The chassis really is the core of this, and you can see that by how many subsequent published geometries I've done. You can see here for the shock upper mounts, I've got one. So somewhere down over here off the right hand side of the screen are a lot of part studios that peel or that pull in or that derive in the references that I'm creating here at the shock upper mount. There's this really simple one for the front bumper, the skid plate, which is we looked at, the side plates are these bumper plates on the side. We'll attach here, and so I need to know the profile along the side is very, very important, and the height and the depth of this profile here. So all of those things. Oh, and then there's a big one with the battery tray, which does incorporate the servo mounting, the servo axis, and a few other things as well. It reuses these same mounting locations from the suspension uprights. So that is what we do in a skeleton model. Then, therefore, let's go over and see how we make use of some of that. Let's have a look at you can see here, actually maybe you can see here a little bit, so you can get a full disclosure of what's in this document. There's a bunch of stuff that is not in this document. Well, we can get to that. But for the most part, I've kept the detail modeling all here just so that I can flip between them easily during this construction phase and detail design phase. Later on, I'll probably show you how I can take these out to their own documents. For the skid plate, let's go to there now. So, like all of these part studios that I create for detail design, I really want to minimize the number of features in here. I mean, it's just so much easier to maintain. It's a fast regeneration. You'll see here, 500 milliseconds. I only have to sift through like a page of features, not 500 features, which become very, very cumbersome to debug and to manage. So, part studio per detailed part is my recommendation. Unless there's a really strong topological relationship between parts, they don't really belong in the same part studio. So skid plate here. The first feature that I use is, as always, deriving from my upstream skeleton. In this case, it's derived from you can follow this thing on the right hand side. It's derived from the chassis published geometry, which is in the skeleton part studio. And what that did, if I roll back, actually, I'll show you what that did. This is what came in, and really not too much. A couple of faces here, and of course there was the mate connector that I've hidden at the moment. But those things are really, really consequential and really, really important to get in. and this early stage. And then you see it's a really, really simple matter of, creating a sketch and doing some extrudes, doing a bunch of extrudes and cuts, and then using hole features to lining up with the references that we already have brought in. I mean, creating holes in these things, and 100% that this hole is going to line up with that hole on the chassis rail, because there is only one reference, and it's the one that you've been passing down. So it's a passing down thing. You don't have to worry about any sort of circular reference, because that's really not possible to do using this technique. I have not come across a way to create that circular reference using the techniques that I'm showing you here right now. So once you do a few more things, and there's probably some more modeling, and maybe there's some light weighting that I could do into here, we're pretty much done with this part studio. There is one other reference that I wanted to show you here, and this is yet another derive of published geometry, and this has come from an external document, which is one of my kind of commercial off-the-shelf things, which is the transfer case. I've got this stored in another document. In fact, I've got a whole bunch of. This is my RC components kind of folder, which has got a lot of interesting documents in it. This one over here, let's load this one up. This is the transfer case. Show all the instances. Yeah, there it is. That's the transfer case, which is sort of, taking from the gearbox, or from the motor in the gearbox, this will actually transfer out to the front and the rear. Anyway, so in here, there's a very, very important interface, which is where this thing is going to need to be bolted. And this is defined by the transfer case manufacturer. Right? And so what I've done and what I've got here is a published geometry which just sends out three very important, well, a few more references. The mate connectors that define where the ends on the axes of the actual axles are, and then the location and mounting holes for the actual transfer case itself. Now these are stored as a published geometry, again as a composite part which contains these references, and this composite part lives with this document. You can see here this part studio contains a number of parts, and it contains this published transfer case. Now, whenever I use this in another design, or in every design that I use it in, I have a robust reference. And you can see it there. So I've derived in that published geometry, and I've placed it where I needed to place it. And now I know exactly where to drill the holes. And I know, without seeing the transfer case, that those holes are going to line up 100% of the time, every time. That is a really, really robust way, and it's a superior way, I believe, to doing it than in some of the other methods that maybe traditionally you would create such things at an assembly level. So here, it's super robust. You can see here, this is the axis and the axle through the transfer case. I can use these for all sorts of fit checks here at this moment as well. That is the skid plate. I did some very similar types of things with these other simple parts, like the front bumper. I used the published geometry, the composite part for this as well. You can see here, so that I know that no matter what happens to the rail, this is always going to fit in, because I've been using these references that have been passed down the chain for me, and that is a super robust way to do it. It's really cool. So I did that. A slightly more complicated one would be the shock mounts. So the shock mounts take in again the from the composite from the skeleton model, kind of losing track of all these different things here. So it's the skeleton model that we created early with the chassis. We did spend some time with that, I remember. And you probably remember these lines, or these construction lines. Now, these have come in from, again, the derive feature of the published geometry. You can see here we are a broken record today, but I can't emphasize enough how good and robust this technique really is. So once I get these references in, then I can start doing some fancy modeling. And this, I didn't make this model in order to flex all of the really cool geometry that we can do in Onshape, but I did use an interesting couple of techniques with routing curves here to create my lattice, and I create these sort of 3D curves around here as well. And what did I do down the back here? Yeah, similar sort of thing. These locations of hard points are lined up exactly with the ones that come from the skeleton. These holes that are placed here line up exactly. It's really, really hard to get it wrong if you use this technique. That's what I'm trying to say here. Now, the most complicated one is these two up, or at least these two or three up here, which are for the axle and the steering knuckle. So let's have a look at the rear axle first, because that's it's more complicated, but it's not the most complicated. Right, there's an old friend staring straight at us right there. That is, again, the published geometry which is being passed down the line of the differential core. And I'm using that in order to create the references. Let's hide it now that it's done its job. You can see in here, these are the position of the bearings, the red surfaces that I've created, where bearings will go. And they fit exactly with the, you can see here, the reason I did that. Also looking at the clearance around here, I made sure that there was an adequate clearance around the ring gear here. Then it was a matter of incorporating some of the other, if I show all the parts, or show all, you'll see here, I don't want the planes. You'll see a bunch of mate connectors which represent the attachment points for the key suspension. And remember these from all the way at the beginning with the chassis skeleton. This is the shock mounting, this is the lower links, this is the upper links, and I think that's most of the links. Okay, and these out here were defined. I'll just quickly go back just so to remind you. I know this is a lot to take in, but I'm pretty pumped with this whole thing. So you can see these same mate connectors here in their really, really abstract, simplified form, but you can see why I did them here. And let me just jump back. Because I can use them. Here's another colored sketch. At least I'm following my own good advice here. So all of these mate connectors are not recreated here. These are coming in from the derived workflows that I'm harping on about. So I know that the center point of these ball joints, which are going to be for the suspension upper links and lower links, will always fit, because there's really only one reference that has been that's been set up here. Right. So if we look at a more complicated one, let's go to the front axle. This is kind of where the really cool stuff came in. Whoops. Still trying to get grips with my space mouse here. And I'm trying to, I don't know why, but I'm wildly gesturing with my other hand, and I'm running out of hands. So some of these really complicated key pieces of geometry, if you remember the kingpin axis, they are being passed down the line, like always, through the skeleton approach. Same with the differential core. We've obviously got a differential at the front as well. I did the modeling for the plate or the cover here. I can see that again. And I'm using some decals in here just because decals always look really good. Now, these pieces of geometry are really, really quite complicated in their angles, and getting these angles right getting the centers of these axes right is, absolutely essential if you hope for your suspension to actually work, not bind up. So again, using these robust references was the only way to do it. And you can see here, again, this is the most complicated Part Studio, which has got still less than 200 features, so it's not crazy. I have a separate Part Studio for the knuckles, because even though everything is kind of related in one way or another, the relations between these is really being defined and maintained by, again, these skeleton geometries. So these kingpin, the axis of the kingpin, the position of the bearings relative to the steering arm, positioned here. All of these things are just being passed down, and I really don't need anything more other than I've used this plane here, or this is the inside of the wheel that I want to use to make sure I've got clearance. That's all I need to then make this a really, really lightweight Part Studio. Again, I'm 100% want to encourage you to not build everything in a single Part Studio. I hate trying to talk people down from that situation. So the good thing is, and we're coming to this right now, is that all of these individual Part Studios and the parts, there's many good things. The first good thing is that we could have done this in a separate document and be working in our own place, in our own time zone, very different situations, but knowing that when we bring it back together, we're going to have a successful assembly. All right. Speaking of assemblies, let's do that. So take you back a little bit to the skeletons. Remember, we had we're looking at the front skeleton, the front details. This was the front skeleton. You can actually make an assembly from this. So this can be articulated. We can have a rear axle assembly of these different components that we had created, and then we can bring them together. So I have brought together the chassis, and the chassis is magically fitting together, and this is already jumped a couple of stages, so I apologize for that, but bear with me. The chassis had the detailed modeling done, and it had a few of these extra components. Remember the front and rear bumper, the tops of the shock mounts. But at this point, I'm going to hide a whole bunch of things. Again, this is sort of retrospectively looking at everything here. So this was the chassis, the rear, and the front axle. So these were the big major skeletal systems. What I want to do is just design the linkages that go in between them. I remember at the start I was going on about the fact that the linkages are kind of going to be problematic because they move a lot, and they're so dependent on absolutely everything that we do in here. So what we do is we build a assembly at the skeleton level. Right, I'm going to show all of these instances and then using an in-context workflow, I bring that skeleton axle. You can see the stuff that's ghosted out here, the rear axle, the front axle, and the chassis. These are the context for which I can start building these really abstracted tubes, which are going to become the linkages that you probably saw in the opening shot. Now, in context is the perfect way to do this as well. And if we change the context, if we change any of the assemblies, then we, because we're changing the wheelbase or we're changing, other angles or suspension heights and things, then all we have to do is update the context, and these things will update. So let's do that. Let's have a look what's going on here. We've changed the assembly somewhat, so we need to update that context. there it is. You can see we changed the length of the wheelbase. So there was a change pending there. If we come back to the assembly now, you'll see that everything is put together perfectly. Now, I have some fastening going on, so I'm going to suppress this, and you'll see here that I can actually move these components very easily. Now, this is one benefit of doing a very early skeleton analysis here. Now, it's a little bit, I'm just sort of dragging this up and down, but you can make this a lot more scientific. Now, these tubes here are representing the shock absorbers, which are sliders, right? So I'm using everything at a very, very abstract level in order to do a very, very early kind of fit and function analysis here. I'm looking for binding in the suspension. I'm looking for tubes of these linkages that interfere with parts of the chassis or other tubes. So I'm getting close here. I think I'm actually interfering up there. So, there's something that I probably need to come back and lower this a little bit more. But again, using this kind of skeleton approach into the assembly now gives me sort of a lot of insight into this, and it's all very robust because it's all hooked together. And I'll put that back down there again. So, because this assembly is back where it was, this we can then update the context and make sure that is. There we go. Make sure that's updated. So that is the skeleton assemblies taken care of. At this point, we've got all our detailed designs. We can start building our detailed assemblies. So the nice stuff is things like the front axle. So I have just brought back together the stuff that we've been creating, and the front axle. These things. I've brought in the core of the differential. These are parts that you can see here linked for outside documents. All of that stuff for the differential. These suspension ball joint caps here. These have come from external standard off-the-shelf components that I've got in that folder that I showed you before. I've got a lot of bearings. This is super detailed. These bearings are actually coming from my catalog of bearings that I maintain, and these are actually fully detailed things on their own, and they're all fully configured, so I can pull out from my catalog just the bearings that I need there. And at this point, it sort of goes without saying that everything fit, right? And I can play around with the steering. And I've actually got limits on the amount of I wanted to see what that limit would be before it would just touch, right? And then I applied a limit on those joints. So when I use this sub-assembly in a top-level assembly, I don't have to worry about it flipping around the wrong way and making the wheels go backwards, things like that. So my decals have come along for the ride, and there's one on the front there as well. Oops, keep forgetting to use the space mouse. It's much smoother. Look at that. Look at that. So yeah, there's a whole lot of detail in here. You can see here, cutting through, these outer bearings, inner bearings there. There's the actual half shafts, and everything's going on in there. So it's. The thing is, though, is that because we haven't gone crazy with 600 feature part studios that are being regenerated every time we touch something here, the speed, the performance, and the usability of this is extremely high. We have a nice detailed rear axle as well. You can see these bearings poking through. We have the detailed version of the chassis, which you kind of got a preview of before. Oh, look, one more sticker, a decal here. And because, and I'll hide some of these fasteners, but the holes line up absolutely perfectly. Again, because we've been using single points of reference for all of those, or the same point of reference. We haven't copied anything. We've just passed them down and derived them down the line. So things like, oh yeah, one more decal. I really like decals too. So the servo, because we used the published geometry from the servo to line up where these holes are going to be and where the fasteners are going to be, everything fits perfectly there. Which then leads us to the top level assembly, which I did start everything out with today. And this is I've been really, I did replace those sliding tubes before with a proper model that I did in a separate document of the shock absorbers. And I've spent a long time with a pair of calipers here and measuring and building these things out, but now I think the payoff is pretty clear. It's pretty cool. I will show, there's a couple of things here. Named positions. Right, named positions are really, really important and very easy ways to keep track of different locations for these joints to be in. You can see here, if I top out the suspension here versus bottoming out the suspension here, I can then come in and then again assess some of the potential bindings. I'm looking here at the drive shafts as well. So let's go back down to the bottom. You don't want these to be binding. Of course, they're not. We can also test some steering extremes. I think there's one here. Yeah, these two down here test the extremities of the steering at the top of their travel. And it's probably a good time to turn the wheels back on. Here they are. And even the body. Because I think I did a deliberate error here. You can see here that the body is actually interfering, so I might need to raise it up a little bit more and make it look even more like a monster truck, or get rid of this lower part of the bumper. Anyway, those name positions are extremely important and very useful things to use for assessing and just robustly coming back to positions of the assembly here. Now I've got a couple of animations that I saved earlier. This is looking at the front suspension up and down. And this is looking at, again, the shocks. This is, showing you how this is fully articulated, right, all the way through the differential, the universals, and the transfer case. All of these are fully operational, and you get some really nice imagery out of this. Steering as well. So again, we're looking at all the different, whether it's the steering, suspension, or the drivetrain, testing all of these things for their fit and finish. And talking of finish, we've come to the end, and this is, it's been a fun model to do. It's been a fun one to talk through, but it's there's a lot more that could go into. In fact, there's one more thing that I did really want to do, and that is, if I line this up and take it out of perspective mode, I'm going to bring in an assistant, which is another browser window, and this is just opening up. You can see there's two of me here. What I'm going to do is go all the way back to one of these global variables. Actually, it's the very, very first one, and I'm going to say, let's make it a 12-inch wheelbase, and I'm going to pass down the line a whole bunch of things, and we're going to go to there you go. So now we've just changed the wheelbase. Everything's updated. that is probably a pretty complicated thing to really make robust for a lot of systems, but you can see the way that I set it up here. I think it's very logical, a very easy way to follow through. And whether you're doing vehicles or robots or machines or any assembly, I think it's well worth looking into this workflow of composite parts, derived top-down skeleton models, and everything else in between that I've talked about here today. Happy to dig into any of the questions you have for this. I know that there's probably a ton of things that were a little bit tricky to follow, but I assure you, conceptually, this is a really, really good and logical way to do things.